Hi everyone, I'm Shaojie, a PhD student from Professor Zhu Zhang's group at Cornell. Today I will present HeteroFlow. This work is in collaboration with my colleagues Xiang, Yuan, Hongzhang, Niansong, Dabjit, and my advisor, Professor Zhu Zhang. To design a high-performance FPGA accelerator, programmers need to leverage different types of hardware customizations. In general, that includes compute customization, like unrolling or pipelining to increase the parallelism. Data type customization, like quantization or fixed point data types to trade off precision with performance. Memory customization, like memory banking, reuse buffer, or data streaming to increase the bandwidth utilization for both on-chip and off-chip memory. In fact, these different types of customization techniques do not just work in isolation. There's a complex interdependence among these techniques. Perhaps the most important aspect of this interdependence is how the data is placed and moved between the custom storage and compute kernels, as indicated using the red arrows in the diagram. We use the term data placement to address this interdependence between memory and compute. Data placement is crucial to performance. However, it is not an easy task to optimize data placement on FPGAs. First, FPGA accelerators employ a complex memory hierarchy. The data placement happens at different levels. Specifically, data placement happens between host and accelerator, between compute kernels inside the accelerator, and for compute kernels implemented with spatial architectures like systolic array. Data placement can happen between the processing units inside the compute kernel. To get a high performance, we should ensure the data of right granularity arrives in the right memory location at the right time. Additionally, data placement does not just work in isolation. To get a high performance, we need to co-optimize data placement with other hardware customizations in compute, memory, and data type. Here, we use image blur as an example to illustrate data placement optimization in HLS. Image blur consists of two back-to-back 1D convolutional kernels as shown in the diagram. Let's take a look at the HLS code with optimized data placement for image blur. HLS programmers need to optimize data placement between host and accelerator by inserting this vendor-specific pragmas. They need to define FIFOs explicitly and connect kernels using these FIFOs for inter-kernel data placement. And to realize a kernel with spatial architectures like systolic arrays, they need to restructure the code and specify the intra-kernel data placement between these processing units carefully. This actually requires a lot of effort and is non-trivial even for hardware experts. As you can see in the HLS code, there's not a unified programming interface for data placement, and data placement is tightly coupled with the algorithm, making the HLS programming model less portable and productive. To address this limitation, we propose HeteroFlow, a new programming model that provides a unified programming interface to decouple data placement from algorithm for FPGAs. HeteroFlow is built on HeteroCell, a popular domain-specific language for FPGAs. HeteroFlow inherits the declarative programming paradigm and decoupled customizations from HeteroCell. Here's a HeteroCell code example. In the algorithm part on the top, we realize the algorithm of the 1D convolutional kernel by declaring a reduced access and the arithmetic operations over this reduced access. Separate from this algorithm part, we can use the decoupled primitive in HeteroCell, like this .unroll, reuse add, or quantize, to unroll the loops, insert reuse buffers, or quantize the data, all in a decoupled fashion. HeteroFlow further extends HeteroCell with this new .2 primitive to provide a unified programming interface for decoupled data placement. This .2 primitive captures the interdependence between memory and compute at different design levels. We will show more details in the following example. We use image blur to demonstrate the usage of .2. We define the algorithm of 1D convolutional kernel in the first function using HeteroFlow's declarative APIs. And then we instantiate two kernels to build a complete image blur pipeline. After defining the algorithm, we create a schedule, which will later be used for decoupled customizations. The schedule is mapped to a target accelerator algorithm here, since a target accelerator platform consisting of FPGA and CPU. Here, since we haven't specified any data placement customization yet, these two kernels are by default inferred to be executed on the host. We can use the .2 primitive to specify data flow between the host and accelerator and offload the application to accelerator. Specifically, in the last two lines of code, we use .2 primitive to move the input image and weights from host to accelerator, and the final output from accelerator back to host. By specifying a data placement, the compute placement is automatically inferred by our compiler. Namely, these two 1D convolutional kernels are inferred automatically by our compiler to be executed on the FPGA accelerator with these two .2 primitives. Furthermore, we can specify the data flow between these two 1D convolutional kernels using .2. For example, here we use the .2 primitive to create an inter-kernel FIFO to pass data between the kernels instead of using a single buffer for data exchange. With .2 primitive, we can also optimize data flow inside a kernel. For the 1D convolutional kernel inside the image blur pipeline, we can choose to map it to a systolic array architecture, which provides higher performance with more PEs and data reuse. To achieve this goal, we first unroll the reduction loop in the 1D convolutional kernel algorithm declaration into an array of PEs. And then we use .2 primitive to broadcast the input data to all the PEs. We further cascade multiple .2 together to propagate the intermediate results across the PE. With the new .2 primitive, we're able to build a weight stationary systolic array for 1D convolutional kernel just using a few lines of code. This is decoupled and is also concise. Compared with other existing programming frameworks for FPGAs, HeteroFlow is the first to provide a unified and decoupled interface for data placement. And by using the .2 primitive in HeteroFlow, programmers can connect systolic array kernels with non-systolic array kernels to build a complete accelerator design. We use this optical flow example as a case study to evaluate HeteroFlow. Optical flow is a classic video processing algorithm. It consists of 8 kernels, denoted by the orange blocks in the diagram. To achieve high performance, we want to offload these kernels to FPGAs and make sure the data placement is optimized at different levels. Specifically, we want to optimize the host-accelerator data placement with data packing to better utilize the object bandwidth, memory bandwidth. And for the inter-kernel data placement, we want to use streaming channel to pass data between the kernels. These optimizations can be easily realized in HeteroFlow. Here is a code example. On the left-hand side, we have the optical flow example to define the algorithms. And then we use the .2 to move the packed data from the host to accelerator, and finally the output result from accelerator back to host. This will be used to generate the optimized HOS code on the right-hand side in the purple block. And for the inter-kernel data placement, we use .2 to connect to kernels. And this will be used to generate the FIFOs and the pragmas to connect the two kernels using FIFOs in HOS. Compared with the optimized HOS code, HeteroFlow program uses much fewer lines of code, and we're able to achieve similar or even slightly better performance compared with the manually optimized HOS code. Additionally, HeteroFlow is portable. It can be easily retargeted to different FPGA platforms with minimal efforts. We use UltraNet as another case study to show HeteroFlow can be used how HeteroFlow can be used to build a complicated 2D systolic array, and how we can use HeteroFlow to connect systolic array kernels with non-systolic array kernels to build a complete accelerator design. UltraNet is an object detection neural network, and it is the winner of DEC SDC Contest 2020. There are 9 layers in total in the network. The original HRS implementation does not employ systolic array. In HeteroFlow implementation, we replaced the 3rd layer with a 4x4 output systolic array, quantized with 4-bit. This will provide more compute power and with more PEs and with better data reuse. And we also fully offload the whole application to FPGA. And we use the data streaming for communication between host and accelerator, and also between the different kernels. Here's the HeteroFlow code to realize the UltraNet. On the top, we have the algorithm definition of UltraNet. And we can use this .2 primitive to create a systolic array for the 3rd layer. Specifically, we first enroll the 2 loops in the 3rd layer into an array of PEs. And then we use the .2 primitive to propagate the intermediate results across the PEs. And furthermore, we can connect this 3rd layer with its previous layer and with the following layers using the FIFO channels. The evaluation results is shown in the table. We're able to build a systolic array for the 3rd layer just using a few lines of code, and we're able to achieve better performance compared with the manually optimized HRS code. To summarize, HeteroFlow is the first programming model to provide a unified interface for decoupled data placement on FPGAs. We provide co-optimization of data placement with other hardware customizations like tiling, quantization, or memory reuse. HeteroFlow provides better productivity, performance, and portability, and we're also open source. Feel free to check it out. Okay, that's all of my presentation. Thank you.